Hi everyone. In today's session, I am going to discuss about carbene ions. What is carbene ion? What is the structure of carbene ion? Then how it is formed? Then what is the stability of different carbene ions? We'll discuss today. It's also one of the reactive intermediate. In last sessions, we have discussed about carbocation and their stabilities. Now today we'll discuss about carbene ions. Carbene ion means what? It is chemical species in which carbon atom carrying positive charge or bearing positive charge and carrying 8 electrons in its valence shell are called as carbene ion. What is carbene ion? Carbene ion is nothing but it is a chemical species which contain chemical species in which carbon contains negative charge and having 8 electrons in its valence shell is called as carbene ion. So like this you can write here carbon, here R group I am writing, here also one R group, here also one R group I am writing. Here for example here 2 electrons are present. Here I am writing that one group, maybe atom or group with less electronegative than carbon, less electronegative than carbon I am writing here. So here it is less electronegative means during this reaction there is a heterolytic cleavage takes place. Heterolytic cleavage. Heterolytic cleavage takes place here. So here lies cleavage takes place because this group is having less electronegativity than carbon, so that the 2 electrons which are present on the bond is moved with carbon and group eliminates from here as positive charge. So this group will get positive charge and here this carbon will get negative charge. Negative charge means how many electrons are present here? These two bonded electrons are present along with carbon only. Here R we can write. This is the carbene ion. This carbene ion is formed by heterolytic cleavage when carbon is bonded to less electronegative group or atom. Okay. Then structure. What is the structure here? How many total number of electron pairs are present, that you have to check once. Here this is a carbon ion. So how many electron pairs? Here this is a bonding electron pair. This is also bonding electron pair. This is also bonding electron pair. This is a negative charge. Negative charge also contain one electron pair which is non-bonding, otherwise lone pair. So that total number of electron pairs, here I am writing total number of electron pairs. Electron pairs are equal to 3 plus 1 equal to 4 I am writing. What is 3? 3 are nothing but bonded. These are bonding. And this 1 is non-bonding. Non-bonding. So bonding and non-bonding. Otherwise lone pairs we should consider in total number of electron pairs. Should not consider pi electrons. Anyhow, here pi electrons are not there. If this value is 4, then hybridization of hybridization of that species is sp3. If hybridization is sp3, then geometry is equal to tetrahedron. This is the geometry, tetrahedron geometry. But here because of presence of one non-bonding electron pair, we should not consider that in shape. Geometry is tetrahedron only. But according to Vesper theory, VSPR theory, the orbital with the lone pairs are not considered in shape. So that here due to presence of non-bonding electron pair, now shape becomes pyramidal. It is just like ammonia. See here, this is was first point. Total number of electron pairs are 4. Then based on that, I written hybridization, type of hybridization sp3, and based on hybridization we have geometry. But because of presence of lone pair of electrons or non-bonding electron pairs, shape, that geometry is deviated from tetrahedral to pyramidal. This is now shape. So here I am drawing This is carbon with negative charge. This negative charge is present in one orbital. This is one sp3 hybrid orbital. Then remaining 3 bonds. Here one R, here also one R, here also we can write one more R. So that this orbital in which this is negative charged carbon. So this orbital in which lone pair of electron is present now, that is not considered in shape. If you close it, the shape becomes this much only. What is the shape here? The shape is pyramidal. It is similar to that of ammonia. It is similar to that of ammonia. This much you have to remember about the shape. Okay. Then stability of carbon ions. Stability of carbene ions. We have different carbon ions: primary carbon ion, secondary carbon ion, tertiary carbon ion, and methyl carbon ion. We have different carbon ions. So first, simple alkyl carbon ions and their stabilities we'll discuss. See here I am telling first one example: CH3, CH3 negative charge. This is the methyl carbene ion. This is carbene, methyl carbene ion. Then here I am writing CH3, CH2 minus. This is ethyl carbene ion, and we can say this is primary carbene ion. Then CH3, C, here CH3, here negative charge. This is isopropyl carbene ion, we can say, otherwise secondary I am writing, secondary carbene ion. Secondary carbene ion. Here this is isopropyl group. So isopropyl also we can say. Then tertiary butyl carbene ion. Here on this carbon there is a negative charge. This is tertiary butyl carbene. Tertiary butyl carbene ion. This is tertiary C minus. This is secondary propyl carbene ion. So, what is the stability order for this? Stability order depends on plus I effect. See here all these groups, here methyl group is the plus I affecting group, here two methyl groups, all alkyl groups are plus I groups. So here plus I effect, plus I effect is inversely proportional to stability, inversely proportional to stability of carbene ions, stability of carbene ions. So this you have to remember. Why plus I effect when increases stability decreases? Because here plus I effect when increases, what happens here? Here it is there is no any plus I group, but here plus I group is there. So when these sigma electrons are shifted to or move to CH2 minus, then here negative charge somewhat developed, somewhat grown. Here because of two methyl groups, here also because of plus I effect, more plus I effect compared to this, here also negative charge on carbon somewhat some more grown or developed. There some more. So that here as per general concepts, after forming any charged species, charge on that particular species must be compensated. More compensation means more stable it is, less compensation means less stable it is. No compensation means it is very less stable. But here what is happening? Instead of compensation, there is increase in the negative charge on carbon, negative charged carbon. So that here plus A effect when increases, stability of carbon ion decreases because negative charge on carbon ion intensifies. So negative charge intensity increases. Negative charge intensity on carbon ion increases, so that stability decreases. So here I am writing due to due to increase due to increase in the negative charge on carbene ion, stability stability decreases, stability decreases. So that here somewhat plus A effect, here plus A effect increases more and more, here still more and more plus A effect increases. So that this is very least stable. Tertiary butyl carbene ion is least stable than secondary propyl, then ethyl carbene ion, then methyl. Methyl carbene ion is more and more stable among these four carbene ions. It is due to plus A effect. Plus A effect is inversely proportional to stability of carbon ions, because the plus A effect intensifies negative charge on carbon ion, or plus A effect increase the negative charge on carbon ion. Therefore, negative charge when increases, then stability decreases. When negative charge decreases, stability increases. So this is the concept behind stability of this normal simple carbene ions. Then, then allyl and benzyl carbene ions. Allyl and benzyl carbene ions. Allyl and benzyl. What is allyl? What is benzyl? Already in previous class only I given. But there about carbocations we have discussed. So allyl and benzyl carbene ions are stabilized by resonance. Stabilized by resonance. So here how these will get stability means it is due to resonance. Even though it is carbocation or even though it is carbon ion, because of resonance they are stabilized. Here there is no inductive effect. See here I am writing allyl carbon ion, CH2 double bond CH, CH2 here minus. This is the allyl carbon ion. It is allyl carbene ion. So when this negative charge shifted from here to here, this bond shifted to carbon. So here we will get resonance form, one more resonance form. On this carbon now we will get negative charge, then CH, here double bond, then CH2. This is one more resonance form. So these two are resonance forms for allyl. So because of resonance, these allyl carbene ion is more and more stable. Similarly, benzyl I am writing. Benzyl, benzyl carbene ion, above benzene ring. Otherwise, this is a phenyl now. CH2 here negative charge. This is a benzyl carbene ion. This is benzyl carbene ion. So it is also stabilized due to resonance only. So whenever this negative charge shifted between this carbon and this carbon, then immediately this bond shifted to this carbon. Why means here already here two bonds, here at this carbon once you check, here two bonds, here one bond, here one bond. Whenever these two electrons which are present in negative charge, when shifted here, number of bonds becomes 5. Carbon will not accept 5 bonds. It is only tetravalent. It can satisfy only 4 bonds around it. So that immediately this bond shifted to this carbon. So here we can get one more resonance form. Here double bond CH2, then here this carbon gets negative charge. These two are already present bonds. Now this negative charge, these two electrons shifted here, so that it will come here. So here we can write one more resonance form. There is here double bond, here negative charge, here double bond, then double bond CH2. In next step, this bond shifted here, then this electron pair shifted to this carbon. Then one more resonance form we can write here. Here double bond CH2, then already present bond. So because of this shifting, here we will get one bond, this carbon will take negative charge. In next step, it will come here and it will move to this carbon. So here the last resonance form for this is like this. Here double bond CH2, sorry, here because this bond is shifted from here to here, so that this CH2 again takes negative charge. Here double bond, here already present double bonds. Like this we have 5 resonance forms. Like this, how many resonance forms we have, including this and last one, 1, 2, 3, 4, 5. So that when resonance forms increases, number of resonance forms increases, stability also increases. So that among allyl and benzyl, among these two, benzyl is more stable. Benzyl is more stable. Benzyl C minus is more stable. more stable than allyl C minus. Why it is so? For allyl carbene ion, only two resonance forms we have. For benzyl carbene ion, only five resonance forms we have. So that benzyl carbene ion is more stable due to more number of resonance forms. And here I'll give one more thing. Here like this, when number of phenyl groups increases on carbon, when number of phenyl groups, number of phenyl groups increases, when number of phenyl groups increases, stability also increases. Stability also increases. So for this I am giving one more example. See here in last previous class, previous session we have discussed about phenyl methyl carbocation, diphenyl methyl carbocation, triphenyl methyl carbocation. Like this here also we have phenyl methyl carbanions. Phenyl methyl carbanions. See here pH. pH is nothing but what? One benzene ring. Means we can write like this. This is which carbanion? CH2 minus. This is phenyl methyl. Otherwise benzyl carbanion. Benzyl carbanion. Like this I am writing here CH minus, here one more phenyl group. This is diphenyl carbanion. Then C minus, here above one phenyl ring I am writing, below one more phenyl ring, this side also I am writing one phenyl ring. This is the triphenyl methyl carbanion. This is diphenyl methyl carbanion. This is just benzyl carbanion. So among these three, which is more stable? Say if it is only one phenyl ring, only one phenyl ring, how many? 1, 2, 3, 4, 5. Total 5 resonance forms are possible for one phenyl ring. Two phenyl rings means number of resonance forms becomes double. Here number of resonance forms becomes triple. So that this is more stable than this one. Than this one. So is benzyl carbanion is less stable than diphenyl carbanion. Diphenyl carbanion is more stable than triphenyl carbanion. So same thing in this way I am writing. pH CH2 minus is less stable than pH taken twice CH minus is less stable than pH taken thrice C minus. So like this also we can write one pH is nothing but one phenyl group. One phenyl group. This is about stability of different benzyl carbocations. Okay. Effect of electron withdrawing groups and electron donating groups on the stability of benzyl carbocation now we will discuss. So here effect of EWG. EWG means electron withdrawing groups, or ERG. ERG means electron releasing groups on the stability of benzyl benzyl carbene ion. Benzyl carbene ion. So when electron withdrawing groups is present, what happens? Electron density increases or decreases. So whenever electron density, otherwise negative charge which is present on carbene ion, when decreases, stability increases. Which groups among these two? Which groups can intensify the negative charge, or which groups can compensate the negative charge on carbene ion? That we have to decide first. So the group which compensate the negative charge will give stability, or the groups which intensify the negative charge on carbene ion will give instability. So here I am writing this example here. First I am taking benzyl carbene ion CH2 minus. Here OCH3. Similarly, last sessions I given explanation, no similar explanation. Here it is para-methoxy benzyl carbanion. You know, methoxy group. Methoxy group. See, this is a key atom. On key atom, two lone pair of electrons are present. So that this is ERG, electron releasing group. Electron releasing group. Why it electron releasing group? Because of it is plus M group, plus mesomeric effect. Here written plus M. Plus M means a plus mesomeric effect. So that here these lone pair of electrons shifted towards this side. So that ring is activated. So through ring, electrons are moving to this carbon. So what is happening? So because of ERG or plus M effect, negative charge intensifies. Intensifies. Negative charge intensifies means increases, intensifies on carbon ion. Carbon ion means the carbon negative charge intensifies on carbon or this is carbon ion. So negative charge intensifies means stability decreases. So this is least stable due to negative charge intensifies. Okay. Negative charge intensifies. Then here I am writing one more. Here CH2 minus. Same thing, but here I am writing methyl group. Methyl group also ERG, but due to what? Hyperconjugation. It is due to hyperconjugation. It is due to hyperconjugation. But hyperconjugation effect, you know, it is not that much stronger. So it is weaker compared to plus M. So that here also electrons are moving towards ring. Ring is activated. Through ring, electrons are moving to carbon. So that here also negative charge increases. Negative charge on carbon. Negative charge on carbon increases. Therefore, it is less stable. It is less stable, we can say. Then one more. Here just benzyl carbene I am writing. Benzyl carbene ion. Benzyl carbene ion. Here there is no any group like electron releasing or electron withdrawing. So here this is more stable compared to this. This is more stable I am writing. More stable. So this is for this ERG hyperconjugation effect. All these for this methyl paramethyl benzyl carbanion. This is more stable due to there is no ERG group or there is no EWG group. Then here, if you observe CH2 minus. Here I am taking NO2. NO2, you know, it is EWG group. EWG, electron withdrawing group, so that it can accept electrons from ring. Ring is deactivated. When ring is deactivated, then that ring can accept electrons from top here, negative charge. So that here, because of EWG, through which effect? Minus M effect. So due to minus M effect, it can accept electrons from ring. Ring accept electron from this carbon ion. So that here electron density, otherwise negative negative charge on carbon ion. Carbon ion decreases, otherwise compensates. Therefore it is most stable among the given. So what is the order of stability? You can write now. This is very less stable than this is more stable than this one, and this is more stable than this. This is the order of stability of different benzyl carbon ions based on their groups, the groups which are present on para position. Here methoxy, here methyl, here there is no any group, but there nitro group. So here lies NO2 group, then CN, then COO, or we can write otherwise C double bond O. All these groups are electron withdrawing groups. All these groups are electron withdrawals. Even halogens also we can consider. Here, all these are electron withdrawing groups. All these groups, what are written here, increases the stability, of C minus. Why means all this can accept electrons from the ring, so that negative charge on carbon decreases. Like these groups, OCS3, then NH2, then OH, like these groups on which lone pair of electrons are present, and even alkyl groups decreases stability decreases stability of downward arrow means decreases stability of carbene ion. So this is about effect of EWG and ERG on the stability of benzyl carbene ion. Next, stability of carbene ions. Stability of carbene ion increases. Stability of carbene ion increases when electronegativity on carbon carbene ion increases. Electronegativity on carbene ion increases. Otherwise, electronegativity means triple bond. Here, example I am taking for explaining this one. CH triple bond C. Here, negative charge. Then CH2 double bond CH negative charge. Then CH3 CH2 negative charge. So among these three, triple bonded carbon is more electronegative. More electronegative. That means this is a carbon ion. Directly, this carbon is carrying negative charge. That carbon with negative charge only having more electronegativity, and this is less electronegative, less electronegative carbon. Here this is not at all means it is normal CH2. Here electronegativity of the single bonded carbon is very very less. Electronegativity of double bonded carbon is more. Electronegativity of triple bonded carbon is more and more. So that here this is more stable than this one and this one. So generally, this the electronegativity on negatively charged carbon when increases, stability also increases. The stability is more compared to normal primary alkyl carbene ions. Then next thing is whenever on carbon, negatively charged carbon, if we take negatively charged carbon, the next carbon means we can say this is alpha carbon. So on this alpha carbon, when multiple bonds are present with more electronegative atom also increases the stability due to resonance. So this is carbene ion CH. Here some groups may be present. So on this carbon there is a negative charge. Next carbon is alpha carbon, but this alpha carbon is with multiple bond with more electronegative atoms. So lysis groups can increase stability of carbene ion. See here, whenever it comes here, it will move to oxygen. So here CH double bond, C here O minus. So due to resonance, this alpha carbon, due to resonance, due to resonance, this carbene ion, this carbene ion is carbene and is more stabilized. More stabilized. These are more stable compared to normal primary carbene ions. Then overall stability. Then I am writing overall stability of different carbene ions. I am writing here. Otherwise, here I am writing overall stability. Overall stability of different carbene ions. Different carbene ions. Overall stability of different carbene ions I am writing here. This you have to remember. So here give different carbene ions. From these they may give 5 or 6 carbene ions in the question, and they ask order of stability, increasing order or decreasing order. Otherwise, among the given, which is having more stability, which is having less stability. Among these, first one is like this: CH triple bond C carbene ion is more and more stable one. Then after triphenyl methyl carbanion. Then diphenyl methyl carbanion. Then benzyl carbanion. Benzyl carbanion. Then after allyl carbanion, CH2 double bond CH, here CH2 minus. This is a allyl carbanion. After allyl carbanion, then phenyl carbanion, C6 H5 negative. This is the phenyl carbanion. Then CH2 double bond CH. This is like vinyl carbanion, similar to this vinyl carbanion. Then after methyl carbanion, CH3 minus. Then ethyl carbanion, CH3 CH2 minus. Then this is more stable than CH3 taken twice. Secondary propyl carbanion. Least stable is tertiary butyl carbanion. Tertiary butyl carbanion. This is the order of stability. So in order of stability for carbocations, tertiary butyl carbocation is more stable. But here the tertiary butyl carbanion is least stable. So all these we have to remember. This is the overall stability of different carbanions based on different reasons. All those reasons just now we have discussed. We have to apply those concepts on these. Then we have to pick up. So here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 I given. So they may include some more also. So by using these concepts, we have to decide which is more stable carbanion, which is less stable carbanion. So this is about stability of carbanions. In next session, we will discuss about free radicals. Free radicals, what is free radical? What is structure of free radical? How they will get stability? All those things we'll discuss in next session. Okay. Up to that, please stay home, stay safe. Thank you.